All right, wonderful. Well, thank you so much for the kind introduction, and thank you everyone who's here tonight to listen to the talk. So today or I guess tonight, I'm going to be talking about some of the work that my group has been doing in additive manufacturing. We're going to be focusing on extrusion-based additive manufacturing for this, and we'll be talking about some modeling we've been doing, some informatics approaches, and then some investigation of new materials, but all focusing on material extrusion additive manufacturing. So I'm glad that folks are excited about additive manufacturing because I'm super excited about it. Polymer additive manufacturing offers a ton of promise and then at the same time a lot of challenges. So there's a lot of a lot of things for us to be looking at as researchers. I've sort of highlighted here some advantages. There's this idea in additive manufacturing where you have this much larger design world. So in additive manufacturing as compared to traditional manufacturing methods such as subtractive manufacturing or things like an injection molding or blow molding where you're doing some sort of forming. You're adding material sequentially, and with that, there's this ability to fabricate structures that have that either couldn't be achieved using traditional manufacturing methods or which would be prohibitively expensive to fabricate. And so some of that is related to this idea that is in this chart where in traditional manufacturing, as you add additional complexity or customization, the cost per part rises exponentially. Whereas in additive manufacturing, it's not exactly flat, but it's certainly a lot closer, where you can have sort of one-off parts that are being fabricated in additive manufacturing. So that's something that is something that's really exciting about additive manufacturing. Additive manufacturing has, I guess, historically been used for things like rapid prototyping. So because you don't need to have the tooling that traditional manufacturing requires, so you could go through the design, test, build cycle for prototyping much more rapidly than you could previously. It's also great for situations where you want to have customization. So there's this 3-axis model of manufactured products that we can also think about manufacturing as living in, where there are these axes of complexity, volume, and customization. And additive manufacturing has done very well traditionally in having low volume parts where you can have high levels of complexity or customization, and so it works very well sort of in that plane. There's been more effort in trying to increase the volume that can be manufactured using these AM techniques, and that's been an area of ongoing interest, so that you can have this high level of complexity and customization in mass manufacturing. So those are some of the advantages of additive manufacturing. There are also a lot of challenges, and those are things that we try to address in the research community. So there is there's challenges related to reliability. So you don't always know if a part that as printed is going to have the performance that you'll need it to have, and so that is definitely a challenge. We have these issues related to reproducibility. So if you end up printing from using different printers, you can end up with different properties, even if you input all of the same parameters and you're using the same material or class of materials, or even you can have everything the same, but then from day to day have reproducibility issues in or even location to location on your print bed, reproducibility issues, and so that's not that's not really tenable as we move towards mass manufacturing. Other challenges related to additive manufacturing come in terms of scale and speed. So being able to rapidly manufacture things over a wide range of scales and resolutions is something that the additive manufacturing isn't great at yet. And so this is the space that we're thinking in often when we're approaching our research in additive manufacturing. Before I move on, I do want to talk a little bit about definitions. You may not have heard the sort of terminology material extrusion additive manufacturing, but this is the standard terminology from ISO ASTM, and material extrusion additive manufacturing refers to additive manufacturing processes in which material is selectively dispensed through a nozzle or orifice. And so this can range in size. If we think about the thermally driven methods from traditional desktop, you can think about like MakerBots or Ultimakers, or Prusas, RepRaps. There are lots of options that are out there for these desktop systems that are also referred to as fused filament fabrication, because you have a filament that's being fed into an extruder, at which point the plastic is heated such that it's in a molten state, and then it's extruded through a nozzle, and then the print head is being rastered in the X and Y dimensions to print a layer, and then the system moves up and you print the next layer on top of that. So that is a very common form of additive manufacturing. And then on sort of the other size scale of so fused filament fabrication is sort of on the lower end, and then we can also consider material extrusion to range all the way up to big area additive manufacturing, or BAM. And BAM is capable of fabricating things that the size of a Shelby Cobra. And so I think that material extrusion additive manufacturing is a fun technology to be investigating, because there's a lot of freedom, and at the same time there are a lot of challenges in how do we make the structures better. So the work that my group does is in combining experimental modeling, informatics techniques in order to better understand processing structure property relationships in material extrusion additive manufacturing. We've done work in sort of these four areas. I'm going to start by talking about some of our work in thermal modeling, and then I'm going to talk about these issues of reproducibility and reliability within a test case, looking at some informatics approaches to investigate material extrusion additive manufacturing. And then I'm going to finish up with talking about some of our work in printing of hot melt adhesives as a new material for additive manufacturing. We've also done some work in irreversible thermal strain, and I'm not going to have a chance to talk about that tonight just for time. But if you're interested in this work, briefly, we've shown that you can print structures out of ABS, or acrylonitrile styrene, very common material, and you can go from, depending on the raster orientation, the layer thickness. Those are the two main properties that are most important. We can end up going from, we can have large expansions and sort of the order of 20 to 30% increases in the height, with shrinkage in the thickness and the width. And then we can also, depending on the raster orientations, we can control the amount of sort of warpage. And so you can see that here we've got a rectangular prism that sort of morphs into this parallelogram-based prism, and we can relate that to the micromechanics of the system. I'm not going to have time to talk about that tonight, but I'm happy to send you some papers or talk about it offline. So today, so we'll start by talking about thermal modeling, because it gives us the opportunity to understand some of the underlying sort of physics of these systems. So we have looked at, we've performed thermal modeling of Maddox systems, ranging from these desktop FFF systems all the way up to the BAM printers. And the principle is the same in all of these cases. We've got some sort of plastic feedstock that's being heated, extruded through a nozzle onto a build plate. But you can see from this table, and also from the fact that this Ultimaker is a thing that can sit on my desk, and then this is me inside of a BAM that's at Oak Ridge National Lab, that the scales are orders of magnitude apart. So typically in FFF, we have layer thicknesses, so that would be the Z direction of on the order of maybe 0.02 to 0.4 millimeters, whereas in BAM the layers are 25 to 50 millimeters. And because of the larger scale and the larger nozzle diameters, the deposition rates for BAM are 3-4 orders of magnitude higher than they are in FFF. And so you can print really large things. And one example is shown here. So this is a Shelby Cobra where the body of the car was actually printed in a BAM printer at Oak Ridge. And so we are interested in thermal modeling in order to be able to predict the mechanical properties in particular of these material extrusion structures. But we've been interested also in understanding how scale affects the dominating physics in these printers. So this is work that was primarily performed by a recent graduate from my group, Tone D'Amico, and so pretty much everything I'm going to be showing here was led by them. In this work, the approach has been to use finite element based approaches in order to perform thermal modeling. What we're showing here is an example of a geometry, and each of these sort of surfaces that are shown in color are an isosurface. So all along one of these surfaces would correspond to temperature. So for example, I think that's corresponding to maybe 90 or so. So this top one, then you can see it gets a little bit hotter as we get closer to this heated build plate that would be at the bottom. And then there's an extruder that's being simulated here, where there's the nozzle that's extruding material. You can see that it's hotter immediately behind that nozzle where material has just been extruded. So our approach is to develop these thermal models, and from these models we get temperature profiles. We get a lot of time temperature information, which is really interesting but a little cumbersome to deal with. And so from there we take advantage of time temperature superposition and polymer weld theory in order to condense that information down to a single number that can give us information about the predicted mechanical properties of these structures. And I'll get into that just a little bit more in a bit later. And from there, we can do B parameterization, so we can start comparing different types of prints and have this sort of number that we can use to compare directly across conditions. Oh, nope. Okay, sorry. I thought I lost the slide. Okay, so people have been interested in temperature profiles in FFF for a long time, and the reason for that is that the structures are extruded in a molten state, and then they have to weld to the previous layer in order to evolve mechanical strength. And if that doesn't happen, you can have delamination, or you can have weak parts. So this time temperature information is important because it dictates how much interlayer diffusion can occur, and therefore what the properties of your part are going to be. So there have been people have been looking at this for close to 15 years. There can be a couple of experimental approaches to this. So sometimes people will use thermocouples. Thermocouples are pretty simple to apply, so that's an advantage, but they'd only get information at one location. Another option is to use IR thermography, and so that's there's been some more recent work that has used IR thermography. IR thermography is nice because you can get information about an entire surface. It does take a little bit more to process that information, and then also you only have information about what's happening at that surface, whereas maybe you want something that you want information about the temperature that's inside of a part. That being said, these data are all really valuable, and they tell us that that these structures are cooling very rapidly during assembly. And so one of the key things you'll see in a lot of the graphs that I'll be presenting is that there's going to be some sort of dashed line or straight line that corresponds with a glass transition. So in amorphous polymers can, if they're have exhibit a glass transition, it's where they go from being in a glassy state to in a rubbery state. And the way that we can think about this is if the polymer is glassy, it's not flowing over time scales that are useful for this manufacturing. Say they can be flowing over years, but to maybe tens of years, depending on the temperature. But really, we need to be above TG in order to have flow. And so so this the amount of time that's above TG becomes really important, and that's why it's highlighted in many of our graphs and many graphs from the literature. What we see is that we've got seconds maybe above TG, so we've got seconds where we can have flow, where we can have enough energy to have interlayer diffusion, to have that strength evolution. That is a very short amount of time, and that is really a fundamental challenge for fused filament fabrication. So we have developed a finite element model that can sort of simulate the print of the printing of polymers in different geometries. What I'm showing here is an animation that of a single road width line. So it's the same geometry as the work from Seppel and Migler, but we've squished it so that there's a little bit more resolution in the Y dimension. And what we end up seeing is that there isn't a ton of variation across the width of the bead, but we do see that there is very, very rapid cooling that's occurring as the material is being extruded. I don't have the details of I'm happy to talk about the details of the simulation with folks if you're interested. But this model allows us to account for conduction, convection, radiation, heat transfer due to mass transfer. What we found is that that for FFF, we don't need to account for radiation, which we'll get into again in just a second, but is convenient because radiation is very computationally intensive. What we are doing here is we're simulating this, this stainless steel nozzle moving across the surface and then extruding material, within that nozzle space. When we compare our simulation to experimental results, we see that without any fitting, that we end up having fairly good agreement in terms of the time scales and the temperatures. What we're doing here is, we're simulating the printing of a single road width wall. This would be sort of a cross section that we're looking at here. And in our simulation, we've got layer 8 being printed, and then this is the temperature of layer 7 as layer 8 is being printed, and then layer 6 is layer 7, or as layer 8 is being printed. And so we see in our simulations, also in the experiments, that there is a little bit of a lag for the lower layers between when they start to heat up from when there is the initial deposition. And that's just because it takes a little bit of time for energy to conduct through the layers. We do see our simulations are overestimating the amount of increase in temperature upon that deposition of the previous layer. And it's also we're overestimating a little bit some of the cooling here, which is related. We think that this is probably due to some of the simplifications we've made in the models, but again we end up having fairly good agreement at this level. So then what we can do is we can take this time temperature information and we can use time temperature superposition in order to calculate an equivalent time at a reference temperature, which we use the glass transition temperature. So time temperature superposition generally states that phenomena that occur over long time scales at low temperatures are equivalent to phenomena that happen at higher temperatures over shorter time scales. And we can, for every sort of amount of time, we can calculate a shift factor, and then we can integrate all of those shift factors across time in our system, and then calculate an equivalent weld time. And so the equation that we're using here, this is the Williams-Landau-Ferry equation, and it works well for amorphous polymers, which we're working with. We're working with ABS here, and so this is an appropriate treatment. And then the reason why it's nice to have a single temperature at a reference temperature, there are two reasons. One is that it's nice to have just a single quantity to be working with. Another is that we can take advantage of polymer weld theory, which is very established and has a lot of scaling relationships for things like modulus or G1C. So your fracture energy release rate is proportional to time to the 1/2, and then things like your strain or your K1C are proportional to time to the 1/4. And so now we have, but it's only isothermal time. And so now we have this isothermal time that we can start to scale our predicted strengths to. We ran our simulations for a range of print speeds, so that's how fast the nozzle is printing the material, and we observe that we end up that we're capable of capturing non-monotonic trends in the time to TG, or the average cooling rate to TG, and we also see the same sort of insensitivity to print speed of equivalent time that is shown in the experimental results. I do want to unpack this just a little bit because there is this kind of interesting balance here. So we end up seeing at really slow print speeds is that we have more time above TG because our nozzle is moving very slowly. So we've got a lot of contact between the nozzle and our print structure, and so we're ending up getting extra heat transfer from the slowness. And as the print speed increases, then we start cooling a little more rapidly. But then at the same time, as we start printing faster, then our layer time gets shorter. And so what that means is that we end up printing. We end up returning to the same XY coordinates, but just at the next layer up more quickly as we increase our print speeds for this case. And so that leads to less ability to cool down. And so there are these competing forces that lead to this local minimum in time to TG in the range of 10 to 30 millimeters per second. I'm showing here a couple of reasons why we think that the simulations are overestimating heat transfer that are due to some of the assumptions that we're making in our systems that allow for more heat transfer between the layers. One of the things that I do want to highlight here is that we've seen in simulations, and it's been shown experimentally that there isn't that the strength of a single weld isn't dependent on print speed. So you can print within this range, which is 3 millimeters per second up to 100 millimeters per second. You can print whatever speed you want, and you get the same strength of a part. And this is because even though we have a longer time to TG out at these ranges, the effect of the higher temperatures and has such a larger time than the sort of the temperatures that are closer to TG. And so that's why we're seeing that, you know, sort of lack of sensitivity to print speed, and then that leads to in a number of cases that leads to print speed independent tear energies. And in fact, what we end up seeing is that extruder temperature, so the temperature that you set your hot end to is far more important for the strength of your part. So all of these, you know, individual colors represent a single extruder temperature over a range of print speeds, and they all kind of collapse onto one another. So that's kind of an interesting thing, and, you know, kind of nice, because it means that in terms of strength, you can just, you know, print faster. You do need to then be more concerned about your resolution, but in terms of strength, that's a variable that isn't as sensitive. I did mention that that we don't account for radiative heat transfer in FFF, and that's just because we've run simulations with it and without it, and we see really small, you know, very minimal changes in the temperature profiles that are observed. This sort of makes sense because radiation becomes more important when you have a much larger thermal mass, and we have really tiny, relatively cool parts, and so it's sort of not surprising in retrospect, but it is a nice thing to confirm. All right, so now I want to move on to talk about BAM structures. So these are the big structures. Again, just to give you a sense, you're depositing at a rate of 36 kilograms per hour. The layer thicknesses are 25 to 50 millimeters, so that's like 0.3 to half an inch, I'm pretty sure. I think I did the conversion right. So these are pretty big layers here. And we see that there is, you know, slower cooling, and that's been observed experimentally. We were interested in extending our model from the FFF scale to the BAM scale, and then doing comparisons across these, because and trying to understand what's important for material extrusion at these different length scales. One of the things that that we see is that the temperatures are just a ton higher. And so here we're simulating the printing of ABS, and we see that that our temperatures are much higher for much longer in these prints. Another thing that we observe is that radiation is super important in BAM. If we don't account for radiation, we get much, our simulation predicts much hotter samples, and then we've got these much longer tails in the as we print. And so radiation is a very important heat transfer mechanism. And there's been some other work in the literature that suggests that radiation accounts for about 30% of heat transfer in BAM. And so that's consistent there. I will say from a practical standpoint, that it's a bit annoying, because radiation is a computationally intensive heat transfer mechanism. In order to implement, we end up implementing it only on this top surface. So as our samples get larger, we have these large sidewalls, and we end up simplifying just so that we can run our simulations in reasonable amount of times. We're only simulating from the very top surface, which ends up being in okay simplification, but it is something that we had to do just to be able to run the simulations in reasonable amounts of time. All right, one thing that that you probably noticed in the in these animations, I can jump back, is that there is a fairly large temperature gradient between the center. So this is a cross section of our print. So between the center of the bead and then the surface. So this would be exposed to air, and we see that that the temperature temperature difference can be at least 10 degrees Celsius, which is a pretty large temperature difference across a relatively small thickness, and so, or I guess width would be the right dimension there. And so that can be a really big deal for warping and for residual thermal stress evolution. So this is something that we need to be considering in BAM that really wasn't a problem in FFF. One of the things that motivated our work in extending our model from the FFF scale to the BAM scale was to try to answer a question that was important in the BAM world. So when BAM was first set up, there were attempts in trying to print with just pure ABS, and the ABS did warped by a large amount. You can see in here, a bar of the BAM printed ABS is warping by about an inch, and so that's not really tenable for large structures to have that much warping, and so then a material was tried that so they were trying other materials and found that chopped carbon fiber filled ABS, which is shown here in black, doesn't warp at all. And so one of the things we were interested in is the chopped carbon fiber changing the chopped carbon fiber alleviating this warping by changing the heat transfer mechanisms, since the ABS filled chopped carbon fiber has a thermal diffusivity that's about twice that of ABS, or is the chopped carbon fiber just acting to resist that warping because the chopped carbon fiber adds more stiffness to the material? And what we ended up seeing is that there isn't, if we look at our isothermal weld times, we end up seeing that there isn't a huge difference between different relative thermal diffusivities that are normalized to ABS. So if we go to ABS, to the chopped carbon fiber, in the center line there is a bit of a difference, but in the center there really isn't. And this and that compares that's very different from what we see in FFF, where there is this local maximum in the weld time at the relative thermal diffusivity that corresponds to that of ABS. And so this suggests for BAM that probably the chopped carbon fiber is stiffening the structure, and so that suggests that other reinforcements could be used, that the thermal properties don't matter as much for that warping, since what the fibers are doing is resisting the warping. So that's was kind of an interesting finding. Another thing to just highlight here are the orders of magnitude. So here we're at like 10 to the 22nd at the center line, and here we're between 10 to the 24th and 10 to the 25th seconds. And so we are a lot so BAM structures have a lot more energy in them as compared to FFF structures, and this is a good example of showing that. Another thing that I wanted to just highlight is this is showing there isn't material being extruded during that part. So just what the iso surfaces that evolve during BAM are really complicated, because these are big structures that are getting rid of heat in a bunch of different ways. And so we've got these there are simplifications that we can make at smaller scales that really start to not be valid in BAM. One of the other things that really starts to appear is the importance of tool paths. So you can see in all of these where we're printing and then returning and then printing another layer and returning. And so you can see that the side that is printed last is staying hotter for longer from the iso surfaces. And so there's a lot to be thinking about and a lot to be looking at here. So just to wrap up this part, so we see that the principles of material extrusion are the same across these scales, but the scale really does affect our dominating physics. Now I'm going to move to the informatics work, and this work was motivated by this understanding, or by this appreciation that even a very simple desktop printer, maybe you've got a hobbyist printer at home, there over 100 adjustable parameters. There are toolpaths that are based on proprietary algorithms. There's a lot of complexity in these in these, even the cheapest printers. And then if we think about the materials, we're using formulated plastics. So, we've got lots of different options. There are different polymer choices, different grades of the same polymer. There are different fillers. So you can have colorants, you can have UV blockers, you can have viscosity modifiers. And then there's also, a batch to batch consistency, which is pretty good if you're spending a little bit more money in getting your filament from a very reputable source. But if you're spending a little bit less money, batch to batch consistency isn't you can't take that for granted. And so there's a lot of complexity, and this is really a challenge for reliability and reproducibility. So this in this project, I worked with this was work that was performed by Dan Ricanier, who did his master's in my group and is now doing his PhD at Northeastern. And so in this project, we just did a 3-printer in-lab round robin. So we used versions of these 3 printers and printed dog bones out of ABS. And we adjusted 4 commonly adjusted print parameters. So we have print speed, print bed temperature, layer thickness, and extruder temperature. So we had 2 levels of each of them. And so we were interested in collecting high quality data, and then also being able to perform some statistical analysis in order to understand what was most important under which conditions. So in order to ensure that we had high quality data, every print was recorded with a print form where we tried to collect all the data that we thought that could be important, and then maybe some other data that was easy to collect. We also collected images of all the prints and representative videos of the toolpaths. The print forms were based in Excel, and then there was a print to PDF sort of thing, so that the data was saved in a non-modifiable format. And then we did a similar thing with the mechanical testing. So when the dog bones were pulled, there was the date of the print, last calibration. I think this is probably date of test, not date of print. My bad. And then the sample ID for each of the samples, the dimensions of each of the samples, and then also the fracture location for each of the samples that was recorded. So what, and then we had a bunch of mechanical data. One of the things that I wanted to that we learned pretty early on was that even though we had tried to acquire ABS that was as similar as possible for the printer, so we needed to have 2 spools of filament, because we had printers that used different diameter filaments. And so we ended up getting the non-colored versions and getting relatively high quality versions. But from here we can see in DMA and then also in DSC that that these materials are very different from each other. One of them exhibits 2 TGs. One's got a very clear single TG. Yeah, they're very different materials. And so some of this gets to what ABS is. So ABS stands for acrylonitrile butadiene-styrene. This is a term that's used to describe a whole bunch of blends and polymers of acrylonitrile butadiene and styrene. And so the most common way that ABS is created today is that there will be a styrene acrylonitrile phase, and then within it there will be lightly cross-linked polybutadiene particles that are grafted with styrene acrylonitrile to help with compatibilization. So even with that, understanding that this is the general form of ABS, here are just some of the variables that can be adjusted between formulations. So there's a lot of complexity here. So even just starting with our material, we had some challenges. I'll skip that. All right. So here we have our strains to failure or strain to failure versus our Young's modulus, and then oh no, I'm sorry. This is our failure strength and our modulus, and then our strain to failure, and then our toughness. And what we're seeing is that for each of these cases, the parameter that was most important was actually what our printer is. And so you can see that the Ultimaker prints are sort of are in this bottom quadrant, this bottom left quadrant. We've got the MakerBot conditions that are clustered up in the top, and then we've got half of our Zortrax here and half of our Zortrax data points here, and that's similar across all the data. And that was really surprising to us. And we think that what has happened is related to how each printer interprets G code. So even though we tried to make everything as consistent as possible, when you tell 3 different printers to make a dog bone, they're going to interpret that information differently. And so here you can see some fracture surfaces of the dog bones, and again we'll get into this issue of toolpaths. So in the Zortrax, there would be a single road sort of wall that was created, and then there would be extrusion in the middle, and it would always start and stop from the same location. Whereas in the MakerBot, there was this more parallelogram that was that evolves because the G code alternated which side you would start your extrusion from. And then in the Ultimaker, the default was to assume that anything that was sort of the dimensions of the dog bone was didn't need to be filled, and so even though we said to fill it, the Ultimaker did not fill that hollow center. So that here we were seeing a lot of complexity in this very simple type of system. I did also want to highlight that in the Zortrax, we see this that extruder temperature is super important. So these are all of the low temperature extruder conditions. These are all the high temperature extruder conditions. Whereas for the MakerBot and the Ultimaker, we don't see that same behavior. And then, so we took this data and we performed principal component analysis in order to try to correlate processing and performance variables for each of these printers. And in principal component analysis, what we have is our primary principal component is being plotted against our secondary principal component, and so each of these are vectors. So there's magnitude and direction that's associated with them. So vectors that are going in the same direction are correlated. Things that are going the opposite direction are negatively correlated. Then we have our inputs in black and our outputs in red. And at a really high level, what you can say is these plots don't look anything like each other. And we can get a little bit into a little bit more detail. We do see that in all cases there was a positive correlation with extruder temperature. We see that there was a negative correlation between layer thickness and our Young's modulus. So in having higher layer thicknesses reduces our Young's modulus. We have some conflicting results for the print bed temperature, and then similarly we have a little bit of conflicting information about our print speed. And so in general, the recommendations would be to increase the extrusion temperature as much as reasonable and decrease your layer thickness. But this also highlights that you can't go from one printer to another, even in the same lab with the same user, and assume that you're going to get anything near the same properties out of a structure, even if you're using the exact same material. So that was kind of an interesting study for us. And then I'm just gonna maybe in like 5 minutes wrap up with talking about some of our recent work in printing hot melt adhesives. So what are hot melt adhesives? Hot melt adhesives are, or where are hot melt adhesives, I guess. So hot melt adhesives are adhesives that they're solvent-free binders, and so they're designed to cool and reach bond strength rapidly and to have good adhesion. So examples of places where you might find a hot melt adhesive would be in your tennis shoes. Hot melt adhesives are used in bookbinding. Also, hot melt adhesives are used in food packaging for like, adhering cardboard boxes together, or also in personal care products. So when we look at those properties, being designed to cool and reach bond strength rapidly and have good adhesion, that sounds like pretty promising for material extrusion additive manufacturing. And so in this work, we've been looking at Technomelt PA, which is a semicrystalline polymer that has a sub-ambient TG. So that means that at ambient conditions it's rubbery, and but it has a high melt temperature, and so this combination gives rise to this transparent, tough, strung material. And in this project, we've been really interested in understanding more about how strength evolves during additive manufacturing of these semicrystalline polymers, understanding what the roles of the crystalline versus amorphous phases are, and then how do we deal with systems that have subambient TGs? So everything we've been looking at up till now has TGs in the range of 60 to 120 degrees Celsius, and so how do we deal with this with these other types of properties? This is work that's being performed in my group by Masi Pirali. And so in this work, we were collaborating with Henkel through an NSF goalie, and they've been kind enough to provide us with the raw materials. So we received pellets. We've been able to extrude our own filament for this, and then we print our structures and characterize them. I will skip through this just for time. What we found is that this particular hot melt adhesive can be printed at a range of temperatures. We can print structures ranging from 150 to 240 degrees Celsius. That said, we found that we get the best properties around above 220 or higher. And actually, what we found is that the mechanical properties of our of the samples at 220 or higher are comparable to compression molded samples, so traditionally manufactured samples. We also see that for samples that are extruded at higher temperatures, that they're optically transparent, which is something that's cool, and they're flexible materials. So we have a lot of really interesting property combinations here. One of the other things that is really odd about these materials is that we see the highest performance, or rather we see the lowest performance in our 0-degree orientation print. So where we're actually filling them, or we're pulling along the road length. Typically the 90-degree orientation is the weakest because that's where you're filling along your weld lines. But here we see that our 45 and 90 have better properties than the 0-degree, and that's something really kind of odd about this. But the properties at 45 degrees and 90 are really excellent, and again are comparable to bulk properties. We think that some of what's happening in the 0-degree systems is probably related to some toolpath related welding issues, where we're also seeing that the 0-degree raster samples have somewhat lower levels of crystallinity. And so the toolpath is affecting our crystallization, which is affecting the tensile properties in these systems. We've seen that our processing and our locations can affect the type and the amount of crystallinity. So our as received pellets start in this purple bar with the relatively high crystallinities. When we fabricate our filament, we see less crystallinity. In our tensile bar, we recover some of that crystallinity. And then one of the things I think is really interesting about this is if we're printing a single sort of cube, when we're printing, looking at the top versus the bottom, we see that there's a lot higher crystallinity in the bottom than the top of this. And so this is another challenge, but maybe also an opportunity if you're trying to think about having gradient properties. This is something that arises naturally from this type of system. So I've talked about the properties being close to that of bulk properties, and we think that a lot of that is because our cross sections are void free. So on the top, I'm showing freeze fractured SEM micrographs, and then in the bottom, we're showing fracture surfaces. And so you can see in the freeze fractured samples that there really aren't any voids, but you can see where the individual layers should be, and we've gotten such good coalescence that these are void-free structures, and then the failure the failed specimens and the fracture surfaces, we're seeing that there's a lot of sort of ribbon-like structure, which is highlighting just how much yielding there is before, how much energy is being uh, absorbed, but before there's the final failure of these structures. So getting to this idea that we have these void-free structures, we think that some of this is because the material has a very low viscosity under print conditions. So we're seeing at a shear rate that is consistent with typical printing conditions. We predict a viscosity of this material of around 45 Pascal seconds, whereas typically for printed structures, the viscosity would be more in the range of 150 or so Pascal seconds. And so we're substantially lower than that. And we think that is helping with this ability to flow while still balancing needing to set up rapidly so you don't get slumping. Oh, that's in there twice. All right. And then I just also wanted to highlight some of the cool things we can do with this. So we can print really large overhangs, and this is a dog bone that's being flexed all the way around. And so these are really neat materials, and this is motivating some more ongoing work in finite element of semi-crystalline polymers, and then also looking at some composites of these materials. So I guess I just want to conclude by saying that we think that material extrusion additive manufacturing is a really interesting area of study, and we think that that modeling and experimental methods combined with doing statistical analysis gives us a lot of information. That being said, there's so much more to learn. And if you're also, I do want to put in a plug. So we collected all that data in the project that Dan worked on. We've also made it publicly available through the NIST space. So if you're looking for some data sets to play around with, I encourage you to take a look at that. So finally, I want to acknowledge my group, in particular the students who perform the work. So I'd like to thank Tone, Dan, and Mossy. I'd like to acknowledge John Sepla from NIST for a lot of conversations. So we used their thermography in order to validate our simulation. So I'm really appreciative for that. For the BAM work that was performed as part of a project with Carter Rock, Oak Ridge, and then the Office of Naval Research. And then the FFF round robin was performed collaboratively with Rob Jensen of ARL. And then I want to thank Chuck Paul, Luca Marchese, and Tim Velters from Henkel for their guidance and recommendations. And then finally, I really want to thank our funding for these projects. The funding comes from the National Science Foundation and the Office of Naval Research. And so with that, I'd be happy to take any questions that folks have.
Awesome. Thank you very much for a fantastic talk. I just learned a whole lot. That was wonderful. So we will go ahead and jump straight into the questions. So first, so are small scales? I mean, based on what you showed, I think that you kind of already answered this, but I'll let you elaborate on it or add anything onto it that you'd like to. Are small scale material extrusion processes generally representative of larger scales, or is there more that you have to consider scaling it up from like benchtop to like the BAM process?
So the principles are the same, and I think that some of the machine design can is similar.
Mm-hmm.
But when you're thinking about what materials and under what conditions you want to process them, that there you really do need to be thinking, um, about heat transfer, for example, and understanding what's going to dominate there. One of the things I do want to highlight is we've looked at the desktop scale and we've looked at the big scale. There is an intermediate scale,
Mm-hmm.
and so I think it's what the gigabit X maybe I think is an example of sort of a medium scale printer that can print things sort of in like the meter by meter by meter range, or there are
Okay.
a couple of examples where um, and for that, depending on how large your extruder is that you're going to be working with, there can be some really interesting intermediate, phenomena happening.
Okay. Interesting. Does the increase? You showed some of the parameters of like the benchtop versus the BAM printers. Does that increase in the nozzle diameter lead to a loss in fine detail that can actually introduce some problems?
So yeah, if you increase your nozzle diameter, your resolution does become limited, and so when we think about there does end up being a balance between you know printing a big thing and then printing with higher resolution.
Okay.
So typically, yeah, examples of the types of things that have been printed really well with BAM would be like tooling for a boat hull, and and then
Mm,
there's a lot of post processing that goes into making the surface what you would want it to be. Whereas with smaller scale extrusion processes, it's possible that you could like fabricate a scaffold
okay.
and not have to do post processing.
Okay, I got you. Are there any larger printers like let's say BAM scale that have say multiple nozzles or anything like that where like they have some that are big for the bulkier pieces that don't have the fine detail, but then they can come back in and do finer stuff, or is it more like you build the bulk of it and then you move it somewhere else and you add in the other pieces?
There is an approach. Yes. Yeah.
Okay.
So there has been some work doing some of that where you can get, to like I'm trying to think, 80 or 90% of the mass of your structure you can do, with a really large extruder, and
Hmm.
then going back in with something that has more fine resolution
Okay.
yeah,
Cool.
yeah.
How bad is or Dr. Kothapali, one of our chatters, wanted to know how much of a possibility of the nozzle getting clogged do you have to deal with?
It depends on the material.
Okay.
Yeah. Yeah, really, it depends a lot on the material. So you can get nozzle clogging with composites fairly easily, especially if you have a relatively small nozzle
Hmm.
size. There are also different nozzle geometries. I'm not sure I've got any good So there are different sort of like hot end designs where you can
Hmm.
have sharper or less or less sharp. Let me see if I can find it. Um, maybe. All right, so there can be a lot of different sort of designs in terms of the angles that are here, but
Hmm.
what can sometimes happen is if there are a lot of sharp angles, you can end up having dead zones in corners. And this is
Oh, okay.
something that is actually like well known from the extrusion world. You can end up with these dead zones where like fluid will just get trapped, and then
Hmm.
because it gets trapped, then it starts degrading, and then you've got like a big, charry mess that's there, and that can cause
Oh,
clogging too. Yeah, so it doesn't
okay.
even have to be a filled system.
That's interesting.
Yeah.
Okay, yeah, yeah, that's. I mean, I would have thought of just, like you said, like coming out through the actual nozzle itself. I wouldn't have even thought about that. That's fascinating.
Yeah.
Let's see. So you talked in your simulations. You had a lot of interesting stuff with how the heat dissipates basically, and how, when you come, depending on how fast or slow you're going, there's heating between the layers, and that can affect how it deposits. Are you aware of any post deposition heating techniques where, whether it's to correct, what you might call a mistake, or if it's like a purposeful part of the synthesis, where people, they do the bulk of the deposition, and they come back in, and heat it to get the material to do something that they want, again, whether it's to fix something, or purposefully to make it form a different shape or whatever.
Yeah, so I know that there's been some research in having having like applying energy to the top surface
Hmm.
of a printed structure immediately before the next layer goes down.
Okay.
So maybe that would be so, and that heat could be like a heat lamp, or I think there's been some work with lasers, and
Hmm.
there's also been some work with trying to I think it was trying to excite carbon nanotubes.
Oh,
So yeah,
interesting.
because then in that previously deposited layer.
I know this is going to be a random question, but I'll explain. Has anybody done anything with like plasmon resonance of metal nanoparticles?
Ooh, I do not know.
Okay, because when you mentioned the carbon nanotubes, it made me think about it, because I know that's I've seen it used for like medical treatments. Like, they'll get the gold nanoparticles into cancer cells, hit them with visible light. It's in the right wavelength, and it generates heat locally, and in that case, obviously, it kills the cells, things like that. But it'd be interesting. Yeah, and it may not be practical. Of course, it's gold, so that's not
Yeah.
really that's not a super practical thing. But yeah, this is fascinating. Sorry, I'm getting.
No, no,
um,
that's neat to think about.
let's see. So Dr. Polly also had a question about, can you use different materials simultaneously in different layers? So I guess it kind of goes back to like the multi nozzle system, for instance. Are there things that are set up like that?
Yeah, there are some systems that are set up like that. I would say if you wanted to have having different materials and different layers does get a little bit trickier.
Hmm.
Just think in terms of so one of the things that I sort of skipped over because it ends up not being as important for similar or for identical materials
Hmm.
is this part of polymer welding, which is the wetting step. And so
Okay.
if depending on the relative surface energies of your material,
Hmm.
then if you have materials that don't want to wet one another, then you'll never get to the step where you start getting reputation
Oh,
and interlayer diffusion.
interesting.
Yeah. But
Okay.
but yeah, so some people do it, yeah. But you need to keep that in mind as when you're choosing your materials.
Okay. Is there anything that could be done, like, I'm trying to think of a good example, something from a ballpark I can speak on. So like when I do some work with Nafion for instance. And so there's certain things where, like, obviously it's fairly hydrophobic, but if you add, say, an alcohol or something like that, it wets at least a little bit better. Is there anything like that can be done, where you can imagine, like, you put one layer down, maybe you put, you have an aerosol spray or something like that comes in, coats that surface, and then that helps bond another material? I know it's fairly exotic, but is it at least feasible?
I would need to think about that.
Okay.
Yeah, I guess so. So another, yeah. Let me think. Um, I guess the question would be, yeah, what are you trying to bond together,
Mm-hmm.
and why?
Okay.
Yeah.
Interesting.
But I guess that's if you're trying to bond together two dissimilar materials, it would be the same. It would be you would have these same types of problems
Mm-hmm.
irrespective of what manufacturing technique you're using.
Yeah.
So yeah, you could probably or you could even do some sort of some chemistry on that surface to get covalent bonding. That would be a reasonable approach. Yeah.
Interesting. Okay. And this next question is kind of along the same lines. One of our chatters asked what the simulation parameters are, and in particular, they're asking about, like, if you use one polymer versus another one, do you have to what kind of parameters do you have to account for when you're working with different polymer materials when you're trying to do these extrusions and builds?
Yeah. So in this in our simulations, we have only been considering heat transfer mechanisms, and so with that in mind, when we move from one material to another, the things that we're changing are the material thermal properties, so things like the
Okay.
thermal conductivity, the heat capacity, those sorts of things,
Okay.
the
Um,
density. Yeah.
yeah. Oh, yeah. That makes sense. With the simulation modeling that you did, I think it was for the ABS deposition. You noted that, like, the trends were very similar, but I guess the numerical values were kind of off.
Yeah.
Um, but you also talked about some of the assumptions that you had made
Mhm.
that likely led to that difference. So, sort of moving forward, what things would you need to do to try and bring those two closer together? Um, whether it's, again, practical or not, it may be another story. But sort of, if you could wave a wand and do something different, what kind of stuff what would you need to do to try and make the simulation match your experimental results more?
Yeah. I mean, so if I look at so this temperature captured at different locations, I think that
Hmm.
the location that we're capturing the temperature at is probably the is more representative of what's actually happening in the weld situation, because we're capturing what's happening in the center of the bead versus on the surface.
Hmm.
That's a pretty small one. I actually the more that we've been working in this world, I think that the one of the bigger sort of areas of where we're overestimating
Hmm.
comes from this very beginning amount of time. So we assume that the extruder temperature
Hmm.
is actually the temperature of the material
Mm.
when it hits when it hits the surface. Whereas
Okay.
sort of you can see here in this experiment that the earliest temperature point that's being captured is 210. So we assume that it's 230 when you have an extruder temperature of 230,
Yeah.
and the first experimental value is 210. And so
Okay.
I think we need to do a better job of understanding what is happening in those very first, like, milliseconds. Or we have an ongoing project where one of my collaborators is doing a lot of modeling of what's happening in the extruder.
Hmm.
And so I think that some of that work will help inform, our simulations and in our modeling, which begins as soon as we come out of the extruder.
That makes a lot of sense, and you're right. That's not something, we always say. Well, we set it at this temperature, but maybe it's not. Maybe it's not
Yeah.
actually that.
Yeah.
That's an important thing. That's really fascinating. Okay.
Yeah,
Pete.
and so if if one of the, and I, because extruder temperature is so important to the, the properties of the result,
Hmm.
the resulting structure, I think that, like, if we're, upon, more reflection and thinking, probably one of the big differences between the different printers in the round robin is, the different hot end designs, and
Hmm.
maybe how they achieve that set point. You can think about different control theory, or maybe you can think about, even just different thermocouple locations. So.
Yeah, the thermocouple especially seems like it would make a big difference because if you have something that's kind of near where the extrusion's happening, but not actually even next to it, you might get something vastly different than what the actual temperature is.
Hmm.
It's interesting. The Pizza Sepulcrate, which is a great name, wanted to know what software you're using for the simulations
We're using console.
console. Okay. Do you think this work could be extended? And this is now I'm showing my ignorance here. Could this work on the polymers be extended to something like extrusion of more metallic materials, or are the properties of those sort of too separated for it to work well?
I mean, we have considered, we are looking at extrusion of filled of 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 filled polymer. So
Hmm.
that would be, um, so that you could consider doing something that would try to replicate something like a metal extrusion for, like a desktop metal, or the
Hmm.
Markforged Metal X system, where there's a polymerish binder that
Okay.
contains your metal parts, and then it extrudes in this similar sort of process, and then that's your green part, and then you go through the traditional sort of binder based subsequent processing with, debines and sintering and whatnot. So
Okay.
we've considered that sort of thing. Um, so yeah,
Okay.
yeah.
Interesting. That's it's neat to see that it can be kind of pushed even beyond what you're already doing with it, which is again fascinating. You talked some about the variability in the ABS formulations that you
Mhm.
actually experimentally measured. So this is more kind of an opinion question for you. Do you based on what you've seen already so far, like you said, between ABS formulations and the way the printers deal with it and all that, if a manufacturer came to you and said, all right, we're worried about these issues, does that variability suggest that a manufacturer should come up with their own recipe, and say, and go to a supplier and say, hey, look, we need you to make this, this way with this build, these components, and cross link this way, or even go so far as to make their own material on site? Or is it something where if you find a reliable supplier, you can count on them to provide the same material every time, and such that you don't have to worry about that as much?
Yeah, so if you were sort of manufacturing this at scale, I would probably assume that you were going to be fabricating your own filament, just because it's a lot cheaper to buy pellets
Okay.
and then extrude your own filament. And then in that case, you can have a lot more, control over, your feedstocks, because then
Hmm.
you can get, a gaylord at a time, and that'll last you for a while.
Okay.
But yeah, and then you would be sort of dealing with with a traditional plastics supplier, that will give you a QA certificate that says this is the thing that you
Hmm.
ordered.
Okay.
So yeah.
All right, very cool.
Yeah.
And then I'll go ahead and say for chat, if you have any last questions, go ahead and get them in now. The last one I have is you talked about how the printers seem to be interpreting the G code differently. Is there again? This is just something I don't know anything about. Is there a standardization of G code across sort of like across all of them? And if not, do you think there should be, or maybe should groups start to work towards it to aid in this additive manufacturing field going forward? Because it seems like if every printer interprets it differently, that's going to make it hard to push some things forward, because everybody's going to have to figure out exactly how their printer interprets everything.
Yeah. So I think toolpath is definitely a challenge. So G code is standardized, but not necessarily how it gets interpreted by how the printer will take that information and then do something with it. And so if you have a more locked down environment,
Mm-hmm.
um, then you don't have as much control over what the printer will do with that information as
Okay.
compared to you can if you have a more open source printer, then writing G code is like writing code, and you can tell it exactly to do what you say, and it'll follow pretty much precisely. So
Okay.
that being said, I think probably the way that the things would go in terms of the future of additive manufacturing in is an industry would
Mm-hmm.
probably be more people having really proprietary tool paths that they know are awesome,
Mm-hmm.
and then having that built into their printer.
Okay. That makes sense.
Yeah.
All right. Awesome. So I'll see if
Yeah,
there's
but
any.
on the research side, definitely I think we need to, there's there can be a lot of variability seen just just based on toolpath related issues.
Yeah, absolutely.
Yeah.
Well, yeah, especially like the one that you showed where it just said, "Well, you didn't tell me to fill in this part, so I'm not going to." And like,
Well,
well,
we did tell it to fill it
that's
in,
true.
but
Yeah.
they said, yeah, but it said, oh, no, that's too small for us to fill in. So,
Oh, okay. Wow,
yeah,
that's even worse. It just said,
yeah,
"Never mind. I'm not going to do what you asked me to do."
yeah. So
Uh,
you can override that if you know
hmm.
what you're looking for, but at the time we didn't realize that that was a thing for us to even be concerned about.
Yeah,
Yeah,
I
yeah,
wouldn't have guessed that. So yeah,
yeah,
I would have expected it to do what I asked it to do. So
yeah. Yep.
yeah,
Yep.
it's interesting.
Yeah.
All right, so I don't see any more questions coming in. So I'll say if anybody has questions, go ahead and get them in real quick. I'll start winding things down. I want to thank Dr. Peterson for coming on. Like I said, it was absolutely interesting talk. Learned a ton. I've got a lot to think about now as well. And so I really appreciate you taking the time to come on here and talk about the work that your group is doing. Like I said, super interesting. It's yet another field that we've gotten to be exposed to, and see the really neat work that's going on. And so, thank you very much for that.
Well, thank you, and thank you so much for having me. I really appreciate this.
Yeah,
Yeah.
absolutely. So I think that's all the questions we've got. And so I will, um, if I can get you to hang around for just a second, Dr. Peterson, we'll chat just real quick. And I'll thank everybody for coming out. And we don't have a talk lined up yet for next week, but I got a couple people I'm talking with. So I'll announce it on Twitter as I usually do. This talk will also be uploaded to YouTube, and I'll tweet that out when it's ready. And thank you all again for coming. And I hope you have a great weekend. Stay safe, wear a mask, and we will see you hopefully again next week. Thanks, everybody.